Okay, this is the module for 5.3 through 5.6. It seems like a lot. There are a lot of formulas, but they're all applied very similarly. So this shouldn't be too bad. Okay. First, we've got the sum and difference identities for cosine. And the idea here is that these work by, or you normally calculate these by finding two angles that sum up to some other unknown angle, and then that allows you to split that single angle into two, which then you can find the trig functions of. For example, we've got this question, find the exact value of cosine of 15. That's not one of our exact values, but we can rewrite it in terms of two of our angles that we can find the exact value of, 45 and 30. Right, 15 is equal to 45 minus 30. So it looks like we'll be using the second formula here, the one that uses subtraction. So to find cosine of 15, we can instead find the cosine of 45 minus 30, because 45 minus 30 is 15. And then we just apply our formula. So the formula says we take the cosine of our first one, our first angle. In our case, A is 45. And multiply by the cosine of our second one. And in this case, B is 30. Okay. And then similarly, we would have the sine of A and the sine of B. So that's all I've done. I've plugged those things in. Cosine of 45, cosine of 30, sine of 45, sine of 30. Hopefully you've got all these values memorized, these trig functions of these certain angles. If not, draw out your table, write out your table, and then just look at it. I think I've got that table on one of these slides coming up. So cosine of 45 is square root of 2 over 2, right? Cosine of 30 is square root of 3 over 2. Sine of 45, square root of 2 over 2. Sine of 30 is 1/2. Then we can just multiply these. In the multiply fractions, we multiply straight across. So 2 times 3 gives us the square root of 6. Multiply our denominators. 2 times 2 is 4. And likewise over here on this second set of fractions. Right, 2 times 1 is 2, 2 times 2 is 4. Right, and then finally, from here, we can add our fractions since they have the same denominator. Square root of 6 plus square root of 2. We can't combine those two parts of the numerator, but we can write them together as one big fraction. Now, there's a tendency to want to try to simplify this further, but this can't be simplified further, right? You may see, well, these are all even numbers, but that doesn't matter since the 6 and the 2 are underneath the radical. We can't just pull a 2 out of that. Okay, to continue using these sum and difference identities, I just want to take a minute and practice writing some various angles here in terms of our standard angles, 30, 45, 60, and 90. You could also do this for any multiple of these angles. I just chose to work with these smaller ones to help kind of illustrate this. So, for example, 75, the first one here, find the cosine of 75 degrees. 75 is just 30 plus 45. So I could rewrite this trig function in terms of those angles. Okay. Right, and then we could plug that into our formula. Okay. 105, let's see. 105 is 45 and 60. So we could rewrite this one as cosine of 45 plus 60. Okay. And then finally, cosine of 15. Let's see, that would be, I would say 30 minus 45. That would do it. So I'd rewrite this one as cosine of 30 minus 45. So these shouldn't be too bad. Just writing any given angle in terms of our standard angles, you should be able to knock that out pretty quickly. As long as you know all your trig function values for these standard angles, applying the formula is just plugging things in, plugging in those individual trig values. So we could continue with these. You'll get practice in that in your homework. They're no different than the one we just did, so I think we're good on that. Okay. The other thing in this section is cofunction identities. I don't want to spend a whole lot of time on these, but the idea here is that each function has a cofunction associated with it. For example, the one we're going to look at here are cosine and sine. Right. As long as the difference in their angles is, well, excuse me, if the angles sum up to 90 degrees, they should have the same trig function values. If you're familiar, if you've been working with these values, these standard values here I've got in our table, you may have noticed while working with these, you may have already kind of gotten an intuitive grasp of this. But the idea here is, like, say, for example, 30 and 60 degrees add up to 90. Well, the sine of 30 is equal to the cosine of 60. Right, I've got that kind of written out over here on the side. The sine of 30 degrees, well, if I take 90, subtract 30 from it, I get 60. So the trig function, the function values here of sine and cosine are going to be equal. They're both going to equal to 1/2. Okay, so this is just kind of formalizing something you may or may not have already figured out. We won't do a whole lot of this, mainly just sine and cosine. We'll have a couple of problems like that to look at. Okay, so I told you these sections are going to be short. They're all kind of a similar vein. We want to write certain trig functions, or sorry, the trig functions of certain angles in terms of other ones. So this could be done, we could do this for the same purpose of what we just worked with, taking two angles and making them add up to one of our standard angles. So the last section was cosine. This section is sine and tangent. There's very little difference here. So I'll just quickly look at this example, find the exact value of sine of 75 degrees. Well, 75 degrees is what, 45 plus 30? Yeah. Oh gosh, how do I skip through these? Now there we go. Right, sine of 45 plus 30. According to our formula, it's the sine 45, cosine of 30, cosine of 45, sine of 30. Again, as long as you know all those values, you should just be able to plug those in. And then simplify. And again, multiply straight across. And in fact, this works out to be the exact same answer as last time. So who knew? Okay. Find the exact value of tangent of 7 pi over 12. I left this one in here. This is the one that the textbook had worked out. Personally, I would not work with these radians. I would convert this to degrees, just because when I look at 7 pi over 12, it doesn't mean a lot to me. If I can convert this to a degree measure, 105 degrees, well, we already actually did that. 105 degrees was, 60 plus 45 degrees? It's just a lot more intuitive to me. Okay. Otherwise, I would say, you could say, so I probably wouldn't skip right from 7 pi over 12 to pi over 3, pi over 4. But you may notice that 3 pi plus 4 pi equals 7 pi. Right, and each of those simplify to these. These are which are standard values for radians. Pi over 3. Oh gosh, what is this? I want to say 60 degrees. I have to think about this for a second. Yeah, 60 degrees, and pi over 4 would be 45 degrees. Okay. Oh, I wrote all over my thing here. There we go. And then once again, just plug that all into your formula. These are our standard angles. You should know these tangent values. I've got them memorized for sine and cosine. If I need more than that, I will have to sit and think and write out my table. Well, let's see, tangent of pi over 3, it's tangent of 60 degrees. Oh, that's a mess. Yeah, I would have to sit and write up my table to see that. That's okay, I've got it right here right for you. So we plug all that in. Not a whole lot of simplifying to start off. I can multiply these two, square root of 3 and 1. It's just square root of 3. And if you remember back in, I believe it was sections 5.1 and 5.2, verifying identities, it's really common to multiply by the conjugate. So instead of 1 minus square root of 3, I multiply both sides of this by, the top and bottom of this, by 1 plus square root of 3. Personally, I don't care if you do that. I am perfectly fine with this answer just the way it is. That's a beautiful answer. I'm very happy with it. Now, if you do work this out, it's actually going to turn out much nicer, but I'm completely okay with this the way it stands right now. Right? But if you work it out, you do get a much nicer picture. Yeah. Okay. Okay, so this one's a little different. We haven't done one of these yet. Now the formula, we're going to work backwards in the formula. So here we've got what A is 40 degrees. B is 160. And let's see, can I skip back to that formula easily? Oh, it's not letting me skip back. Okay. Let me erase that and go forward with this. And there's our formula. This was the difference formula. So what we're going to be doing is taking the sine of our first angle minus our second angle. And the reason for doing that, that's 120 degrees, or sorry, negative 120 degrees. And that's one of our standard angles. Well, excuse me, it has a reference angle. That's one of our standard angles. Okay. And so we can find that exact value. Okay, so wow, we're just speeding right along here. So there's a lot of kind of redundancy here. Double angle identities can be used for a lot of the same problems we just did. More often than not, when you take a calculus class, the purpose of these is to write one trig function in terms of multiple trig functions, kind of split them up. Maybe you've got a product like this, you've got two things being multiplied. That can be kind of tricky to take the derivative of or to integrate. So instead we want to write that as a single trig function. So there are a lot of uses for these. I always kind of think of it as just playing around with trig functions. When you got something, you're working on it in calculus or some other advanced math, you just want to kind of find a formula that looks like it and kind of play around with it, rewrite it in a slightly different way. Our problems, for the most part, are pretty straightforward. You'll be given one thing and asked to find the other. It can get slightly more interesting. Maybe they give you this right side. Maybe they'll give you cosine, and they ask you to find the cosine of twice that angle. Okay. So let's do a couple of these. So here's that kind of example. We're given one of these values, cosine of theta is 3/5. Can I get a finer pen? Yes, I can. And it asks us to find the sine of double that angle. So I've got that relevant identity right here for us. The sine of the angle of twice that angle, we're going to need 2 times the sine of the original angle times the cosine of the original angle. And fortunately, we've got this second part. We've got the cosine of A. They gave us that. The question is, what the heck is the sine of that value? There are a lot of ways to find it. I would say, well, my personal favorite is to look at this and say, okay, if cosine is 3/5, well, if you recall, cosine is x over r, so we've got these two values. And now I could find y using the Pythagorean theorem. Y is r squared minus x squared. And I take the square root. I realize I skipped a step there. Right, the Pythagorean theorem starts off x squared plus y squared equals r squared, and I just solved that for y. So plugging in everything, r is 5, so we plug that in and get 25. X was 3, we plug that in and get 3 squared is 9. 25 minus 9 is 16. And we can take the square root of that and get 4. Now that we've got y equals 4, we could find sine. And then we're looking at the original angle theta here, so I should probably write that. So sine of our original angle is y over r. So that's 4/5. So now we've got that part too. So we could just multiply these two together. Okay. So I've got 2, right from right here, the 2, times the sine of our angle, and I actually found it, it's 4/5 here. Times the cosine of our angle, and we were given that 3/5. Multiply this out, multiply our numerator straight across, we get 12, 5 times 5 is 25, and that gets multiplied by 2, so that's 24/25, and that should do it for us. One thing to keep in mind here, I guess, I should have been more careful about that. They tell us that the sine of this angle is negative. They say sine is less than 0. So really up here when I took this square root of 16 really has two options. It could be positive 4 or negative 4. Right? Either one of those, when we square it, we get 16. In our case, we wanted the negative value. Doesn't make a difference. You really could have done this at any point in the problem. If the sign, as in plus or minus sign, is off, look for that. Anytime you take the square root of a number, it could be positive or negative. Make sure you're choosing the right one, and you should always be given some kind of clue like this to tell you which one to use. Okay, now that I scribble all that in, I'm pretty sure that's already written on the slide. Yeah, so there are all the steps written out for you. There I used a different, instead of the Pythagorean theorem, I used the Pythagorean identity. So a slightly different way of doing it. We still get that same sine value. Sine is negative 4/5. And then applying it, well, it's the exact same. We did that just like that. Cosine, you could do the same thing just with the cosine double angle formula. I won't walk through this. I mean, it's essentially the same thing we just did, except we already know the sine value is -4/5. Okay. Plug everything in, combine like terms, all that stuff, and we're done. To find the tangent of 2 theta, there are a few ways of doing this. The first one is to use the formula, using our new double angle formula. And in order to do that, we have to find tangent. And we can do that because we know the sine and the cosine. We spent some time doing that. And since tangent is just the division of those two things, we divide them and we get our -4/3, which we can then plug into this formula. Okay. There's an even easier way to do this. I mean, plugging in, it should be pretty straightforward. This one I like even more. If we've spent the time to find sine of 2 theta and cosine of 2 theta, well, that's all we need. You know, our reciprocal, not our reciprocal, our, oh gosh, no, I can't remember the name. Our big identity for tangent, it says whatever that angle is, even if it's twice some angle, we can find it just by taking the sine of that and dividing it by the cosine of that. And since we spent all that time finding those values, we might as well use them. Okay. Okay. Okay, so here's an example with all 6 of these worked out. We've done all these independently. Again, here I'm using the Pythagorean identity. Well, that's not the Pythagorean identity. That's my double angle identity. Okay, but not significantly different, so we'll just kind of skip over that. Here, same as before, but I've just drawn it. I've drawn this thing for you in the coordinate plane, so you can kind of see it. Okay. Using these formulas, we can go backwards with them as long as you can recognize which identity they are. So the first one is our double angle identity for cosine. Cosine squared of an angle minus the sine squared of that angle gives us cosine of twice that angle. And really, this needs another set of parentheses here. We're taking the cosine of all of that, which is going to be the cosine of 14x. Okay. All right, part B, sine 15, cosine 15. Oh, see, I didn't even recognize this. In order to use our double angle identity, we need a 2 in there, and we can get that using this trick of multiplying by 1. I almost took this problem out, but in reality, we do this a lot in calculus when we're integrating. If you need some number in there, like I need a 2 for my formula to work, what I do is I multiply by 1. Why did I write it like that? Right, in the form of 2 over 2. You know, 1 equals 2 over 2. And then I could rewrite 2 over 2 as 1/2 times 2 over 1, or just 1/2 times 2. Another way of thinking about it, if you needed some number in there, you would just multiply by that number and divide by that number. Very common trick when you move on to calculus. Okay, once we've done that, now we can use our formula for 2 sine of 15 cosine of 15, which is the sine of twice that angle. right? Twice 15, 2 times 15. And that 1/2, that just gets carried down and it's going to get multiplied by our final answer. Final answer, jeez. Okay, so sine of 2 times 15 is sine of 30. And the sine of 30 is square root of 3 over 2? No. Well, that makes sense. 1/2. I'm thinking of, is that right? Yeah, sine starts at 0. Yeah. So sine of 30 also happens to be 1/2. We multiply by that 1/2 that we had out front. And then just multiply our fractions straight across. 1 times 1 is 1. 2 times 2 is 4. Oh my gosh. Okay, one last set of formulas. And again, I know I'm kind of rushing through these. Any of the examples that we kind of skimmed over, you've got the notes on them. I'll also post the Pearson videos on those as well. For the most part, these should be pretty nice to recognize. In most of the cases I'm going to give you, because, I mean, you just choose the formula that looks like the one you want. If I've got a 1/2 out in front, cosines being added or subtracted, sines being added or subtracted, well, you would know to use this formula. Okay. Write for cosine 75, sine of 25 as the sum or difference of two functions. So finding the right one of these, we probably could have used a few different formulas here. Did I choose the wrong one of these to write down? What am I missing here? Yeah, this isn't the right formula. For sine, when this is a sine, then these are both sines. And in between them we're subtracting. Wow, that's a mess. But you can see we've got that actual formula down here. Okay, but we've actually plugged in those values. Okay. So I copied the wrong one of those. That's okay. We've got the correct one used here. Yeah. So we've identified A and B. A is 75. B is 25. Because those are the angles that they gave us. Right? So we can just plug A and B into our corrected formula. Right. Okay, and that's what I've done here. With the 4 out front, since we didn't want the 4 there, we just kind of pushed aside. Notice I've got everything in parentheses, and I just carry that 4 down throughout the problem until we've simplified everything inside the parentheses. Right, I added 75 and 25 together to get 100. Right. Now I can deal with that 4. What I did is I just multiplied it by this 1/2. 4 times 1/2 is 2. And then I distributed that 2 to each of these. And then we were done. Okay. Sum to product identities. So we're taking a sum and writing it as a product, or we're taking a difference and writing it as a product. Again, just another set of formulas. You just find the one that looks like what you're given or looks like what you're asked for. So using sine of 2 theta minus sine of 4 theta, I didn't write the actual identity, but here it is once it's plugged in, where I've taken A is 2 theta, I've taken B B is 4 theta, and plug those in. Now this one will simplify pretty nicely. Right, 2 theta plus 4 theta is 6 theta. 2 theta minus 4 theta is negative 2 theta. And these will simplify. 6 divided by 2 is 3. 2 divided by 2 is 1. So cosine of 3 theta times the sine of negative theta. We could play around with this a little bit more. With sine, you can pull that negative sign out, and we would be done. I would be okay with leaving it like that. You know, that's perfectly fine with me. And finally, half angle identities. These are actually just the double angle identities that have been solved for one of the half angles. Right? So it's the same formula. It's just been kind of written. So an example of this. Find cosine of 15. So this is what I was talking about. There's a lot of redundancy in these sections. There are a lot of ways we could find the cosine of 15. And that's the same as cosine of, 60 minus 45? Did I do that right? No, 45 minus 30. Right, we could have probably done this with a double angle formula of some kind. Maybe not. We definitely could have done it by taking the difference of 45 and 30. Okay, but if we're asked to do this using a half angle, what we're going to do is we're going to say, okay, well, if we let A equals 30, then A over 2 is 15 degrees. So in our formula, look, A over 2, that's going to be 15 degrees. Right? And then all this over here, 1 plus the cosine of A is 1 plus the cosine of 30. Okay. Simplifying that, here I've spent a lot of time on the algebra, so if you're having trouble with algebra, you can kind of look through some of these steps here. Cosine of 30 is square root of 3 over 2. What I did from here to here, first off, notice that we're ignoring the plus or minus there. What we did is they told us that, well, it actually didn't even tell us. They told us the angle is 15, and we know that's in quadrant 1, and so sine has to be positive. It has to be greater than or equal to 0 in quadrant 1. So I just ignore the plus or minus. I just chose the positive value. Second, the actual calculation. What I did is I took this 1, I divided it by 2. I took square root of 3 over 2 and I divided that by 2. And when you do that, this 2 just gets multiplied by this 2 to get 4. Okay. All right, and from there we can come up with a least common denominator to add these two. Least common denominator would be 4. And I rewrite that first term. I just multiply the top and bottom by 2. And now I've got the common denominator. Now I can add the numerators. 2 plus square root of 3 over 4. And then finally, we can't do anything to simplify the numerator. There's a lot going on up there, but we can't. We've got like, these aren't like terms. One is underneath a radical. One is underneath 2 radicals. We can simplify the bottom. We can take that square root of 4, and that's 2. And notice that my root no longer extends down to the bottom. Okay. Tangent, again, same idea. 22.5, dividing that by 2 is not going to help me, but how do I want to say this exactly? This is kind of the result I'm starting with. I'm saying, okay, A over 2 is 22.5. Yeah, that's my half angle, which means doubling that, multiplying by 2 Well, cancels the 2 over here, and we see just a. And 22.5 times 2 is 45. So that's kind of where you're starting at. You're looking at this angle and saying, well, what can I do to it to get one of the numbers I want? If I multiply that by 2, that gives me 45. That's a nice, easy angle to work with. And now we've got a is 45, a over 2, 22.5. So we can plug those things in. I guess we would plug in our 45 here as well. Right, so plug it all in, and then plug in those known values. Again, the algebra here is the messy part. There are a lot of ways of simplifying this. The one I've done is I say, if I've got 2 fractions here, they both have the same denominator, they both have 2. If I multiply the top by 2 and the bottom by 2, that will get rid of both of those fractions. And I can get away with that. We already talked about this, because 2 over 2, that's just 1. Multiplying by 1 doesn't do anything to change our problem. Okay, so when I multiply that on the top, it's really easy. This 2 cancels with this 2 and leaves us with just the square root. On bottom, we have to distribute this to both of these terms. So we get 2 times 1 is 2. And here it cancels with this 2 and leaves us the square root of 2. Once again, I am perfectly fine with leaving this just the way it is. However, if you multiply by the conjugate, so take 2 plus square root of 2, multiply by 2 minus square root of 2, this really cleans up nicely. Okay. What the heck? This is displaying strangely.